Okay, so now it's recording. This is week 5 written homework problems. This is buoyancy, drag, this type of unit. So hopefully we can address some of these problems and figure them out. Alrighty, so we got problem 1 here, right? Problem 1 is running and drag. So it says when running outside, there is a drag force due to the runner moving through the air, right? My bad, hold up. I'm looking at a different homework, my bad. When running or walking, there's a static friction force on the runner because the runner's shoes are not sliding against the surface of the ground, as they would if you tried to walk or run on ice with skates on. There's also an inertial drag force as the runner moves through the air. All right, so we have static friction force on the runner because the shoes are not sliding against the surface. So this kind of goes back to the idea of static friction force being the force that keeps you from slipping, right? So it kind of gives you that grip force on the ground, and that's why static friction force is applicable when you're driving a car too, because those tires kind of grip the ground, the road, right? It gives you static friction force that kind of propels you forward. And there's also an inertial drag force, so F drag, and we don't necessarily put like an I or a V to indicate, actually, well, yeah, we kind of do, I guess. So FV is like viscous drag, I'm pretty sure, and then I guess if you want to put Fi for inertial, it's up to you, but yeah. So we have F drag, and that's inertial, right? And now part A is asking us in the space below to draw and correctly label a free body diagram of someone running outside at constant velocity pointing to the right. So first we want to start off with a little circle here, right? You want to draw a free body diagram, someone running outside at constant velocity. So we have that static friction force, we have drag, right? Those are given to us. What other forces are acting on this person here that is walking or running? Normal and gravity, right? So we have normal force pointing upwards like this, gravity pointing downwards like that, right? And then what are the directions for static friction force and drag? So static, this one is a little bit weird here because in reality, let's say you're moving to the right, right? Like this problem says, you're moving constant velocity pointing to the right. Well, if you have your static friction is supposed to be propelling you, right? In the x direction, your drag, think about that. It's kind of weird because like when you have drag is always opposing your intended motion. So if I'm trying to move to the right, that drag is going to be pointing to the left, actually. So I think about that as my, quote unquote friction. Like that's how you think about it, because like drag would be pointing this way to the left, but static friction force, because static friction force is that kind of grippy force that helps propel you forward, right? It's gonna actually be pointing to the right, which is a little weird and a little abnormal, I guess, in a sense, because you're used to, for example, if you have a block sliding across a floor, you're used to the kinetic friction, for example, pointing in the opposite direction to the velocity, right? So if I'm trying to move to the right, you're used to the kinetic friction force, for example, pointing to the left, opposing that motion. But in this case, static friction force is a little bit different when you're running, right? If you're walking or running, that friction force helps you move. The friction force is actually kind of like your F push, quote unquote, right? It's the force that helps you propel forward, that helps you walk in that direction that you're trying to go to. So when you're using friction to help you move, that static friction force specifically static friction force is going to be in the direction of your motion. But yeah, so kind of imagine it as if, like, basically if you had your foot here on the ground, you had your shoe, when you walk, right, you're kind of like pressing on the ground to the left. You're pushing, like, think about like you maybe grinding your foot on the floor or on the ground, right, or on the road when you're running. So you're kind of having your foot come in contact with that road or that floor, and you're kind of pushing backwards. So it's almost like your actual motion is pushing backwards, and so the static friction force is pointing to the right to kind of propel you forward. Does that make sense? because your foot kind of like, when you run, right, your legs kind of like go behind you, right? So when you're running really hard, for example, your legs kind of almost, I guess, I don't want to say like flat behind you or something, kind of like a tail, but basically that's the idea, where it's like you're kind of pushing backwards. So imagine like a horse kind of galloping. You kind of see those their legs, right? They're kind of pushing backwards almost on the ground, but that static friction force between their hooves and the ground, right, between their legs and the ground, kind of pushes them forward in the direction that they want to go into. So that's the difference kind of in the direction notation when it comes to static friction force. Static friction force is actually pointing in the direction that you're trying to move in, right, when you're in motion, kind of when you're walking specifically, and you have kind of a grip between your leg and the ground, or between the tire and the ground, those types of situations. Does that make sense? So I think of static friction force as kind of like a grip force, whenever there's kind of a grip between you and the ground. So like if your shoes have traction on them, the sole is kind of like really grippy, right? Kind of helps you grip with the ground. You're kind of pushing backwards on the ground, and then that static friction force, that grip force, kind of propels you forward. So that's why you have your static friction force actually pointing to the right in this case, and your drag force pointing to the left, because drag is always going to oppose your motion. So in this case, like drag would kind of be like your friction, and your static friction force would actually kind of be like your push force, pushing you forward, basically. That's the informal way of thinking about it. So that being said, that's your free body diagram. Hopefully that makes sense for everyone. So we cool to move on to part B? Okay, cool. Part B is the runner experiences a drag force with magnitude F drag is equal to 0.3 kilograms per meter times v squared when running. If the runner has a cross-sectional frontal area of 1.5 meters squared, what is their drag coefficient? And we have the density of air is 1.2 kilograms per meter cubed. So we have density, right? So with density, right, you have this little rho here, right? I'm not one for Greek letters. I don't know why, but I guess it just kind of makes it a little bit easier and simpler to kind of remember this stuff, because once you get to like things with pressure and stuff, pressure and density kind of both look like P's. And so rho here is the Greek letter that we use for density. And so I just tend to call it fancy P. So rho is density. It's kind of like an italicized P, if you will. So it's like, that's what I like to call it. Fancy P is your density, or rho, right? And now that's our density, and that we have is 1.2 kilograms per meter cubed. We have our area is 1.5 meters squared, right? And our drag force is equal to this section here, right? Now, we know that our drag force, right, that's going to be equal to, what is it? I believe 1/2 times the drag coefficient times the density of your fluid, right? This is, let me kind of draw it a little bit more fancy, right? This is your rho, this is your density of the fluid, times your area, right, times v squared, right? That's your equation for drag there. And so since we have this equation here, we have our area, we have our density, we can start to solve for our drag coefficient. So we know that the drag here is equal to 0.3 kilograms per meter, right? And then times v squared. And we can set that equal to half the drag coefficient times our density, right? And that's 1.2 kilograms per meter cubed. And then we can multiply by our area, which is 1.5 meters squared. And then we have v squared here at the end. right? So you can see here that v squareds will cancel out. We don't need to know the velocity here necessarily, or the speed, so we kind of cancel those out, right? And then we have 0.3 on this left end here. We have half, we have the drag coefficient, we have 1.2, and we have 1.5, right? So you can kind of divide these two values over, multiply by 2, and you should be able to get your drag coefficient. V squared is on the left side of the equal sign as well, because drag force here is equal to 0.3 kilograms per meter times v squared. Yeah, so that we're using, like, this is your normal equation for drag, right? But they also told us that drag just happened to be equal to 0.3 kilograms per meter times the v squared. So essentially what you're looking at here is that 0.3 kilograms per meter is equal to this part right here. So half times your drag coefficient times your density times your area, that section here is equal to 0.3, and then we multiply it by v squared. So that's the idea there, is that they're trying to take this equation and give you, like, group all of these values together, half CD, PFA, right? Group them together, and then that value is 0.3. And so we just have to put 0.3 times v squared on the left-hand side here, and then solve for CD, right? Your drag coefficient right there. Does that make sense so far? So let me rearrange this stuff and make a little bit more room here. So if we multiply by 2, 0.3 kilograms per meter times 2, because we multiply over this 2 here from the 1/2, and then we can divide by 1.2 kilograms per meter cubed, and then we also multiply down here by 1.5 meters squared, and then that should give us our, and then we said we canceled out the v squareds here, right? Because they're canceling out. And then this should be equal to your drag coefficient. So let me know what you guys got for your drag coefficient there. Should be pretty small. Yep, 0.33. Sounds about right to me. Yeah, and drag coefficient, yeah, it doesn't have units, I'm pretty sure. And you can think about drag coefficient, right? If you're into cars, I guess, a really low drag coefficient should mean that the car, for example, or the vehicle is more aerodynamic. Really high drag coefficient means that the vehicle isn't very aerodynamic. So if you watch a lot, or if you look at those, like, Tesla ads, often, like, you'll see that they advertise a really low drag coefficient, so the car is supposedly really aerodynamic, for example. So, but yeah, that's some real life, I guess, context there for what drag coefficient is. But yeah, does that make sense for B? Okay, sounds good. So part C now is asking, if the runner has a mass of 56 kilograms and is running outside at 4 meters per second, we need to find the drag force she experiences. So we have mass of 56 kilograms, right? And she's running with a velocity of 4 meters per second, right? So we just need to figure out the drag force, right? We know that F drag is that 0.3 kilograms per meter, right? And then we know our velocity is 4 meters per second, and that's squared, right? Because it was 0.3 times v squared. And so you just multiply those two together, and I believe we should get 4.8 newtons there for our drag force. But yeah, makes sense for part C as well. It's very simple. I'm not even sure why they really gave us the mass here. Really don't need it because you're just figuring out the drag force, and drag force would just be equal to 0.3 kilograms per meter times your v squared, whatever her velocity was at 4 meters per second, and you square that. Sound good for C as well? Yes? Okay. Now for D, I think that's our final part here. If the runner is pushing her shoes against the ground, generating a friction force of 11 newtons, find the greatest speed she could reach running outside. So, thing is here, if we're looking for the greatest speed she could reach, right, and we have this drag force acting on her, right, this greatest speed actually refers to a concept called terminal speed. So if we're looking for the greatest speed she could run with outside, when drag force is acting on her, the greatest speed she can run with, right, is when the drag force is equal to the other forces in the x direction, or if the drag force is in the y direction, for example, would be equal to the forces in the y direction. So whatever force drag is in, like whatever direction the drag force is in, then if we have x, right, then the other forces in the x direction should balance it out and cancel it out. So when we have our greatest speed or our terminal speed, it's when F drag equals all the other forces, or when all the other forces cancel out in that specific direction, right? And so that's when your F net is 0 in that direction. So when F net is 0 in the direction that drag is pointing in, so in this case F net x, right? F drag, when you add it up to the forces in the x direction, right, and that's the only other force we have is static friction force, right? And that drag should be equal to that static friction force. And from that, we can figure out her fastest speed. So once again, terminal speed when drag force, right, is equal to basically the other force in the same direction. Or to put it more clearly, not necessarily the same direction, because we're not negative x, we're looking for just the x direction in general. The other forces on the same axis. There. That's a better way of putting it. Yeah, terminal speed, terminal velocity. And velocity is speed with a direction, so terminal speed is the same as terminal velocity. It's just at least magnitude of velocity would give you your terminal speed in that case. So like if the terminal velocity was like negative 15 meters per second, then your terminal speed is just 15 meters per second. That's all. And technically here, like with this equation, the drag equation here where we have v squared, v here is actually going to be the speed. And the reason why is even if you were to have like your direction be like negative, like if you had your velocity be negative 14 or something, right? Like if we had that she was running to the left at negative 4 meters per second, it doesn't matter anyway, because when you square it, you're always going to get a positive value when you square something. So like if you do negative 2 squared, negative 2 times negative 2, that's going to give you positive 4, right? Negative 4 times negative 4, that's going to give you positive 16. Whatever you do, when you square it, you're going to get a positive answer. So like that's why they put that value there as speed anyway. It doesn't matter, because once you square it, you're going to get speed. So yeah, I mean, in that case, like I said, terminal velocity, magnitude of that is your terminal speed, basically. So yeah, terminal speed is when your drag force, right, will equal the other forces on the same axis, right? So if we are talking about the drag force pointing in the x-axis, then we're interested in static friction. If we're, for example, if it was a bullet, for example, shot directly downwards in the water, right? A bullet was traveling downwards this way, then we're interested in drag here pointing in the y direction, right? And the other force is pointing in the y direction. So that in that case, that would be like, well, I guess drag wouldn't be pointing downwards, my bad. Drag would be pointing upwards of drag if you were in the y direction, and you have your gravity pointing downwards. So we'd be interested along the y-axis. So we'd set up an F net y equation. But since it's pointing in the x-axis, we have our F net x, and we know that when our drag force is equal to the other forces on the same axis, then we have an F net of 0, and that's when we have our terminal speed or our greatest speed. So we have our drag force, and then minus the static friction force, right? And so in that case, Fd should just equal Fs prime, right? The static friction force should just equal your drag force. And then from that, we know that drag force is 0.3 kilograms per meter times the v squared part. And then our static friction force, they said, pushing her shoes against the ground generating a friction force of 11 newtons. So this is just equal to 11 newtons. And then we can solve for v, right? So we divide 0.3 by 11 here and then take the square root. Let me know what you guys get for that. But does that make sense with the whole terminal speed and when you have a terminal speed? Or is it still a little bit confusing for some of you? Mm-hmm. Yeah, so F net is 0 because we're interested here in the problem. They're asking us to find the greatest speed she can reach running outside. And so that greatest speed, right, occurs, or essentially that greatest speed or that terminal speed occurs when your drag force is equal to the other forces on the same axis. So when we're looking at the drag force, yeah, go ahead. Yep, exactly. They would cancel out. Because the idea of terminal speed, like that term terminal means like final, end, right? So when you think about like axon terminal would be the end of like the nerve basically, right? So if we're looking at terminal speed, then when your drag force is equal to all the other forces on the same axis, your net force is 0, right? Because if for example, we had drag force, we had static friction force, and we had like an F push force, for example, right? For example, something like that, right? And then we know that your drag force is equal to like these other forces, and they would cancel out to have an F net of 0, right? And so we're interested in the speed. We're not interested in the actual drag force at the moment. We're interested in what the speed is. So we know that the drag force is 0.3 times v squared, and that's equal to your static friction force, and then we just figure out the terminal speed from there. And when we say terminal speed, right, pretty much once that drag force equals the other forces on the same axis, right, that's the fastest you can get. So she'll just continue moving at that point at that same speed forever, basically, once she reaches that terminal velocity or that terminal speed, right? Yeah, and if they were just asking what the drag force would be in this case, then drag force is equal to static friction force, so drag force is equal to 11 newtons. Yep. Yep. Mm-hmm. Yeah, I don't know why they put it up here, like within a part specifically, because I remember like when I started reading this problem incorrectly, for some reason I was looking at my old homework because I had that pulled up just in case the homeworks were different, and so I was reading off my old homework, and they had the drag force like here, they stated that in the actual context of the problem from the beginning. And so I'm not sure exactly why they would put it here in the middle when you actually need it for the rest of these problems, but it is what it is, I guess. But yeah, hopefully that makes sense for problem 1. I don't know if someone gave an answer for what the terminal speed was, but I think it should be around like 6.06 meters per second, something like that. Sound good for problem 1 for everyone? Okay, cool. So that's problem 1. It's a good warm-up, I guess, because problem 2 is, I mean, if I wanted to say what I am thinking about problem 2, I'd have to like censor this video on YouTube. But yeah, problem 2 is something else. So it took me a minute to kind of, figure things out. I mean, the individual parts aren't bad. It's just that I think I was messing up the free body diagram initially. So problem 2, life in the slow lane. Bonus points if you can tell me which band had a song called Life in the Fast Lane. Feel free to post that in the chat if you want, if you're wanting to make this session a little bit interesting and fun, I guess, because solving physics problems isn't always fun. Like, this is not what I do or like to do in my free time. So, but yeah, with this problem, we have a microorganism. The microorganisms, like bacteria, have evolved to develop flagella that help propel them in water. The figure on the right shows a simple model flagellum that uses rotary motion to apply a continuous push to the fluid, right? From Newton's third law, the fluid pushes back on the bacterium. This equal and opposite force, labeled F thrust, right, propels the bacterium forward. Once the bacterium starts to move, a drag force from the surrounding fluid opposes its motion, right? In the case of bacterium, small object moving slowly, it is the viscous drag that is relevant. So, well, before we start with the problem, I see 2 answers here for what the band is. I have Dave Matthews and the Wiggles. So, still waiting on a right answer there, but we'll see. We'll see if someone gets it. But anyway, there's a lot of information in this really huge paragraph here, right? We have F thrust. This force is propelling the bacterium forward. So that's kind of like our push force, quote unquote. F thrust, right? Now, technically, this flagellum, the way it kind of functions is that it pushes back kind of on the fluid. So it pushes kind of this way, and that helps the flagellum kind of propel forward with that thrust force, right? So they say that the rotary motion applies a continuous push to the fluid. From Newton's third law, the fluid pushes back on the bacterium, right? So if we're pushing on the fluid this way, then the opposite but equal reaction, right, would be the thrust force that we feel. Now, for part A, they're asking us to draw a free body diagram, right? Now, we know that there are a couple forces here that are in play. We have that F push force, and then we have the thrust force, right? Is there buoyancy? Absolutely. There is buoyancy. So your first instinct there was absolutely correct. There is buoyancy because we're underwater, right? Because this bacterium is swimming in water at a constant velocity, right? It says pick the direction of the velocity in the positive x direction, include both horizontal and vertical forces, and for simplicity, assume that the density of the bacterium is about the same as that of water, which would make the buoyant force equal to the weight in this case. So they kind of simplified there, gave you 2 forces right there. So viscosity is like more of a property than it is like, I guess, a force. But yes, there's viscous drag. So, I mean, that factors in viscosity, right? when you're calculating your Reynolds number and stuff. But yeah, I mean, we have our drag force, we have buoyancy force, we have gravity, right? And we have a thrust force, right? So gravity is pointing downwards, that's classic, right? And then we have buoyancy force pointing upwards. And they told us that the buoyancy force is equal to the weight in this case, right? So this object is kind of basically in a neutral buoyant position because it's underwater, it's submerged underwater, but the buoyancy force is equal to the gravity. So like, let's assume that in that case, if the buoyancy force is equal to the gravity, then we don't have any motion in the y-axis direction, right? We're not experiencing any net force in the y direction. But there is thrust force, right, to the right. And then what else do we have? We had the drag force, right? The drag force would be opposing our motion to the right, because we said the velocity is in the positive x direction, so this is positive x moving to the right. Drag force would oppose that to the left, right? Now, the mistake that I was making earlier, that I'll just point out, is the fact that whenever you're drawing your free body diagrams, make sure to only include forces that the object is feeling, right? Only what the object is feeling, right? Why? Because if you think about it, when they were talking about Newton's third law there, they said that the fluid pushes back on the bacterium, giving you that thrust force, but that rotary motion is actually pushing to the left. So like, if you think about it, there's actually like a F push force from the bacterium's flagellum, right, onto the fluid to the left. But if you have two forces pointing in that negative x direction there, right, it kind of makes things a little bit weird, because then you would think, for example, that, oh, maybe there is a net force to the left, for example, or something like that, right? Because if F thrust is supposed to be equal to, but opposite direction to that F push that the flagellum is exerting, then F push plus F drag will overwhelm the thrust. So you would think that there would be a net force moving to the left. Exactly, right? But since when we're drawing our free body diagrams, we're only concerned with what the object is feeling, not what it's exerting, just what it's feeling. That's why we only draw drag and we only draw thrust. The bacteria is only feeling that thrust force, right? That opposite force, but equal in magnitude to the F push that it was exerting. And it's also feeling the drag force due to the fluid. It's only feeling drag and it's only feeling thrust. We don't include what it exerts. So include what it feels, not what it exerts. That's when you're drawing your free body diagrams, right? So that's the mistake I made earlier, because I was really confused. I was like, well, if there's a net force to the left, shouldn't there be movement to the left? But we're only moving in the positive x direction, so it wouldn't make any sense. I forgot my own rule and my own understanding that, once again, when you have your free body diagrams, only draw forces that the object is feeling, not what it exerts. So, with that being said, that should be our free body diagram for part A, right? And so we have this F thrust is equal to your F drag. Buoyancy is equal to your gravity. And the reason why we have thrust is equal to your drag, the magnitudes are equal, is because the water is moving at a constant velocity. What does constant velocity mean? Yep, excellent, no acceleration. Yeah, absolutely right, no acceleration, so there's no net force, because F is equal to ma. If acceleration is 0, then we have no net force. Having no net force doesn't mean that the object is not in motion, because we could still be moving at a constant velocity, right? Constant velocity indicates no acceleration, but by the definition of a net force, right, if acceleration is 0, then the net force is 0, right? So we can still move, it's just that there might not be a net force, right, that is giving some kind of acceleration to the object. So that's why we have to have, or draw, F drag is equal to F thrust, right? Now, with that being said, we can probably move on to part B, but is everyone cool with part A there? Yeah. The constant velocity means 0 acceleration, so that's why when you do your F net is equal to ma, right? If zero acceleration, then you have zero net force, and that's why your forces should cancel out. Yeah, for FB because you don't have a surface of contact here. You don't do normal force, and so yeah, you use F buoyant force, right? You use your buoyant force there because you're underwater. Yep. So yeah, if everyone's cool with part A, then we can look at part B. So part B, it says, assume the bacterium is a sphere with a diameter of 1 micrometer, swimming in water at a constant speed of 30 micrometers per second. Right, so we have our constant speed, 30 micrometers per second, diameter of 1 micrometer. Density of water is 1,000 kilograms per meter cubed, and the viscosity of water is 0.001 Pascal seconds. Compute the magnitude of the viscous drag force on the bacterium. Express your answers in piconewtons. Recall that a piconewton is equal to 10 times, or 10 to the negative 12 newtons, right? So, what's the equation for our viscous drag here? I think it would probably just be easier to say it out loud instead of using the chat, because there's probably going to be some variables that you guys might not be able to write properly in the chat. Anyone want to give it a shot? No idea. Okay, that's totally fine. No worries. All right, no idea. Thanks for being brave though. Like, at least, like, you said that you didn't have any idea, so we can go over that. So that's good. But our viscous drag force is going to be equal to 6 pi times our viscosity. Viscosity is kind of like an N kind of thing. I don't remember what the Greek letter is, but I'm not good with Greek letters, but let's just call it fancy N. It's kind of like this, whatever. And that's times the radius, and then times our speed, right? So 6 pi fancy N RV. Let's call it that, right? That's your viscous drag force. Well, we know the viscosity is 0.001 Pascal seconds. That's our fancy N there. Our radius, well, we have our diameter, right? So diameter is equal to 2 times the radius, right? So we just divide the diameter by 2 to get our radius. And then, let's see here. Okay. Yep, absolutely. You'll convert your micrometers to meters. You're 100% right, because we want all this to be in meters, because Pascal's the foundational unit for it. Will have meters in it, right? So we want to make sure all our units are kind of in meters, and that way we can then convert things properly to piconewtons. So now we have 6 pi, our viscosity, times our radius, times our speed here. For diameter, right, we can say that this was, what, 0.5 micrometers is our radius, right? Because we just divided the diameter by 2 to get our radius. So there's 0.5 micrometers. And then 0.5 micrometers, well, we know that in 1 micrometer there are 10 to the negative 6 meters, right? And so in terms of meters, your radius would be 0.5 times 10 to the negative 6 meters. So we have 6 pi times our viscosity here, 0.001 Pascal seconds, times our viscosity, which is 0.5 times 10 to the negative 6 meters, right? Did I miss anything? 6 pi, yep. And then our constant speed, 30 micrometers per second. Same thing there. We'll do 30 micrometers. I want to write it here just so because I don't have a lot of space. Or actually, 30 micrometers times 10 to the negative 6 meters. That's 1 micrometer. Micrometers will cancel out. You'll be left with meters on the top. So then our speed is 30 times 10 to the negative 6 meters per second. We can multiply all this stuff out. And what should we get for our viscous drag here? Yeah, go ahead. I mean, you would multiply by, well, I guess, yeah, I mean, you can divide by 1e6, because then that would be the same as multiplying by 1e to the negative 6. That's kind of weird, but yeah. I see. I mean, what you can do here, I mean, you can literally just put like 30 times, what is it, 1e negative 6, and then you'd be able to get it that way. But yeah, I mean, I'm not really a fan of doing the whole e stuff for some reason. I just like to write out times 10 to the negative 6 or whatever on my calculator. I just feel like it just kind of, I don't know. I can see the numbers there, so it confirms everything for me. But if you're able to convert them properly, I believe you should get, 2.8 times 10 to the negative 13 newtons. Sounds about right to me. Yep. 2.8 times 10 to the negative 13 newtons. Yeah, for sure. Using the E function is more appealing, I guess, and it saves you a lot of space for sure. But for some reason, like, I'm just like against E when I'm calculating, because I feel like if I have to like put in like a negative sign or something, right, when I'm multiplying, if I do like 1e negative 6, the E, since like there's like 3 lines to the E, right, like for some reason I'm like always worried that I'll like not notice the negative sign there because it's like so close to the E, and so I'll just look at it and be like, oh, that's just a long E, and then mess up like my values and stuff. So yeah, I just honestly just prefer to like multiply out with the tens and stuff, even if it means screwing up my space and for it to be a little long, as opposed to seeing like a long E. Yeah. But yeah, I mean, I've gotten good at using my calculator often to write out 10 to the negative something, that honestly, like, the amount of time I save is negligible at this point if I use the E function. But yeah, 2.8 times 10 to the negative 13 is about what you should get. I love how we're like all discussing about like how we plug in 10 to the x on our calculators. Like everyone has a preference. But yeah, whatever works for you, as long as you get the right answer, like that's the most important thing. I mean, honestly, like the whole idea here is that you should have your micrometers cancel out. You should have 0.5 times 10 to the negative 6, and you kind of plug that into the whole thing. I wouldn't even like worry about like calculating what this is individually. I would just straight up just like cancel out these units and then know that 0.5 micrometers is 0.5 times 10 to the negative 6 meters, right? And then I would just like go ahead and just plug in 0.5 times 10 to the negative 6 into the greater equation and then figure like out my final answer there. I wouldn't even be worried about like finding what the individual value is, because then you just have a lot of different parts and then you might mess things up when you try to plug them back in. But yeah. Yeah, that's viscosity. Yeah, I mean, once again, the way they have these problems structured, you'll need density, but later on in the problem, there's no reason for us to find out like anything using density in this specific part here. But eventually you'll have to figure it out, or use it essentially for a different part of the problem here. But yeah, if everyone's cool with B, we can probably move on to C. So yeah, go ahead. Oh shoot, you're right. I forgot about that part. Thanks for pointing it out. So yeah, we do have to convert this to piconewtons. Forgot that part. And so for newtons here, right, we have 10 to the negative 12 newtons is equal to 1 piconewton. So my newtons cancel out, and I have piconewtons on top, and I know that 1 piconewton is equal to 10 to the negative 12 newtons. But yeah, and then that, let me calculate that out real quick. Actually, I don't think you even need to. Plus negative 13 plus 12, that should give you like 2.8 times 10 to the negative 1, basically. So like 0.28 piconewtons, I believe, if I didn't mess up that math. Because negative 13, like when you have any exponent that's negative up here, it'll just kind of, you just look at the exponents, it'll be like negative 13, and when you divide exponents, you subtract them. So it'd be like saying like negative 13 minus negative 12, and that's negative 13 plus 12, and that's negative 1 for your exponent. But yeah, 0.28 piconewtons, I believe, is your final answer there. Thanks for pointing that out. Sorry about that. But yeah, very rarely do they ever like want you to convert it to a specific like other unit, like piconewtons, kilonewtons, whatever. Because at that point it's just like they already know that the exam or the quiz is difficult as it is, so there's no point in like messing you up even further with any additional conversions. But just be prepared for that to happen, and also be prepared for you to not have that value given to you. So they might not even tell you that a piconewton is equal to 10 to the negative 12 newtons. So that's another thing for the exam, is to always be sure to memorize like all your like suffix or prefixes and suffixes, right, and stuff like that. So yeah, they always, I mean, I will refrain from saying anything about the administrators for the course here, but generally, let's just be neutral, and I'm just going to say it to be weary of that type of stuff, because you just have to watch out for the now I'm just losing my train of thought because I'm like worried. Okay, you guys got me tripped up. Let's see here. Yeah, so just be wary of like the prefixes, like so your kilo, your mega, delta, or delta. See, now I'm at deca. That's what I meant. Deca, deci, centi, that type of stuff. Make sure that you're wary of that, because it'll probably pull that stuff every now and then on a quiz, on an exam. So hey, keep that in mind in case that they don't give that to you. But yeah. Anyway, I think that should be your answer for part B. If we want to go over like the prefixes real quick, like usually the ones that you have to know is deci, centi, milli, micro, nano, pico. Deci, centi, milli, micro, nano, pico. Deci starts off 10 to negative 1, right? Negative 2, then negative 3. So it goes 1, 2, 3. And then they start increasing by 3, basically. So 10 to negative 6, 10 to the negative 9, and 10 to the negative 12. That's how I memorized them real quick. Deci, centi, milli, micro, nano, pico. And then it goes 1, 2, 3, and then you start increasing by 3. So 3, 6, 9, 12. But yeah, fair enough for the units there. I know that there's probably an acronym somewhere out there. You'll probably find it on Reddit or something, especially for students who are studying for an exam like the MCAT or something like that. There's bound to be acronyms and ways to memorize them. I don't know. I'm not an acronym kind of guy usually. So just deci, centi, milli, micro, nano, pico, 1, 2, 3, 6, 9, 12. There. But yeah, we can move on to C now. So, how much force do the flagella of the bacteria need to generate to propel it at the above velocity of 30 micrometers per second? Well, this kind of goes back to the idea of constant velocity, terminal velocity, terminal speed that I was talking about earlier. Well, since we said that our F thrust is equal to our F drag, because the flagellum or that bacteria is moving at a constant velocity. What did I say earlier about our drag forces being equal to the other forces along the x-axis, or along that same axis that the drag is pointing in? What did I say earlier about that? It's equal to axis forces, so F drag would be equal to the F thrust, but more specifically, kind of in a broader context, yes, we reach terminal velocity when the forces on the same axis are equal to drag force. So when they cancel out, right, they're equal to, or at that point you would have the terminal velocity. So like as long as thrust force is like bigger than your drag force or something, like you would be kind of moving at some speed, you might be increasing. The more you increase your speed, the greater the drag force gets. So like imagine like if you're moving, trying to like walk through like in a pool, for example, right? If you're just kind of walking along, right, you might not feel that really huge resistance on you, right, by the water, that drag force from the water. But then as soon as you start like running or something, like if you're playing like, I don't know, if you're playing basketball, right, in a pool, and you start running, for example, to get the ball, then if you try to run at that really high speed, right, you're going to feel a lot more of that resistance, because once you're trying to increase your velocity, when you're trying to increase your speed, as you increase it, that drag force increases. And so once that drag force increases to a point that is equal to the other forces on that same axis, on that same direction of motion that you're going into, that's when you've reached a terminal velocity. So there's a point where like, okay, I can't run any faster than this, right? I've reached my maximum velocity of 30 micrometers per second. That's my terminal velocity. Terminal means like ending or final, right? So when I reach my terminal velocity, this maximum velocity, it's when that drag force has increased to such a point that it has fully canceled out the other forces along that same axis. So when that drag force is fully canceled out the F thrust force, that's when I see a terminal velocity. Now they've happened to tell us that, yes, that bacteria is now moving at a constant velocity. So if constant velocity means, that your acceleration is 0. So your net force is 0, right? If net force is 0, then F drag is equal to F thrust. So it's kind of like setting things equal to each other, right? So if constant velocity, that constant velocity means acceleration is equal to 0, right? Or I'll say means acceleration is equal to 0. Then F net is equal to ma. That means that F net is 0. If F net is 0, then F drag is equal to F thrust, or all the other forces along the same axis. And if F drag is equal to F thrust, right, then the velocity that we were moving with is equal to terminal velocity. And so, with that being said, this 30 micrometers per second is that constant velocity, that constant speed from part B, and that constant velocity, like we kind of determined here, where we kind of switched back and forth in terms of like setting things equal to each other, that constant speed, that constant velocity of 30 micrometers per second is your terminal velocity. And that happens when your F drag is equal to your F thrust. So if we're looking at how much force does the bacteria need to generate to propel it at the same 30 micrometers per second, well, we just need to figure out what like thrust force, basically, right? That would be exerted, right, or that the bacterium would feel to propel it at that 30 micrometers per second. And that F thrust force is equal to F drag when we have that terminal velocity, or when we have F drag equal to F thrust, or all the other forces along the x-axis. That's when we have our terminal velocity. Our terminal velocity is our constant velocity, and our constant velocity here is that 30 micrometers per second. So essentially, we're just looking for, we know that the F drag is what? F drag, that viscous drag, was that 0.28 piconewtons, right? We want to figure out the force that is needed to propel. That propelling force was the F thrust, right? So we need to figure out F thrust. So what would the F thrust be? Technically, you don't even really need to set up a F net equation to figure things out. It's the same thing, right? So yeah, absolutely. F thrust would still be equal to 0.28 piconewtons, right? Because that thrust force is equal to that drag force. When they're equal, that's when you experience that constant velocity. That's when you experience that F net equals 0. That's when you experience that terminal velocity. That's the idea. Does that make sense? And if you wanted to set up as an F net, we can do F net equals 0, right? And that's equal to F thrust minus F drag. F drag is equal to F thrust. F drag is equal to 0.28 piconewtons, and that's equal to F thrust. Sound good? Yeah, no, absolutely. You, like, for any of these problems, write an F net equation, please. Like, always write an F net equation if you're trying to figure out forces and stuff like that. I'm just saying, like, in general, like, if we were just kind of think about this, like, from a logical thinking perspective, like, we don't even have to, like, do the math and stuff to figure it out, to notice that if F drag is equal to F thrust, then F drag is equal to, or F thrust is equal to 0.28 piconewtons. But yeah, you're absolutely right. Please, please, please write your F net forces, write out the whole equation, do that to get all your points. And once again, when you're doing your free body diagrams, right, here they didn't tell us to indicate X and Y axes or something like that. But if they ask you to do that on an exam or on a quiz, just literally put Y axis, X axis, like that, to label it. And if it's like on an inclined plane, right, where we had those block problems sliding on a ramp or something from the last couple of weeks, you have to put you literally, do exactly what I'm telling you to do. Do a little asterisk, put tilted coordinates, right? And then draw that tilted coordinate. Literally draw this. Like, literally draw Y and X like that at a tilted angle. If you draw that, you're going to get points. If you don't, you're going to lose points. From what I've seen so far, like, people are losing around like half a point to a point max for not labeling axes if they're required, or not labeling that there's a tilted coordinate system. So please do that. But yeah, that's part C. Part D now is computing the weight of the bacterium, assuming it has approximately the same density as water. So it says, how does the weight compare with the forces from parts B and C? Given your answer, which of the forces in the free body diagram are too small to be significant? Well, we know that weight is equal to force of gravity, right? And that's equal to what? Our density of the bacterium times the volume of the bacteria times gravity, right? Well, we're already assuming that the density, what was it? They said it here in the problem somewhere. He said, assume that the density of the bacterium is about the same as that of water. So your density here, your fancy P, your rho, should be 1,000 kilograms per meter cubed, right? Your volume, you can figure that out here in a second, but our gravity is 10 meters per second squared as usual, right? So how do we figure out the volume? Look here somewhere for any hint of how to figure out the volume. So, sure, I mean, if we had density, that's equal to mass divided by volume, right? But do we have the mass? So someone said in the chat here, we have an indication that the bacterium is a sphere, right? And we have access to a diameter. So knowing that the object, that the bacterium is a sphere, well, we can find out the volume of a sphere. The volume of a sphere is, make sure to note this because sometimes you'll get sphere-related problems, but usually they'll give you the equation for it. But a sphere is 4/3 pi r cubed, I believe. Yep, 4/3 pi r cubed. So that's the volume of a sphere. That's the volume of our bacterium. So we just need the radius. The radius, we already figured out, that was that 0.5 times 10 to the negative 6 meters. So knowing that the density of the bacterium is around the same density as water, that's 1,000 kilograms per meter cubed. Our volume is 4/3 pi times 0.5 times 10 to the negative 6 meters, and that's cubed, right? And then times 10 meters per second squared. That should give us our weight there. Let me know what you guys get for your weight. And then based on that value, we have to determine, like, okay, how does that force value, how does that weight compare with the other forces from parts B and C? Because parts B and C, we can see that there's what? We said that this viscous drag force, right, was 2.8 times 10 to the negative 13 newtons. We saw that we know that the buoyancy is equal to the gravity anyway. Our thrust force is still equal to that 0.28 piconewtons, right? That 2.8 times 10 to the negative 13. But 1,000. I think I should. I got 5.24 times 10 to the negative 15. Believe that should be correct. Anyone want to dispute that or check, or anybody else get the same answer? That's what I got, but I just like to double check in case I messed something up. Same? Okay, cool. Cool. Alrighty. So, with that being said, that's our problem 2 there. Done and done. Hopefully that made sense for you guys. Still no answer on who has a song called Life in the Fast Lane, but well, there we, okay, finally, someone got it. Yes, the Eagles. There we go. Ding, ding, ding. Yeah, that's the right answer. Yeah, you do be Googling things, though. So, um, oh, shoot, yeah, we do have to compare for part D. So, yeah. So, we have our drag force that's 10 to the negative 13 newtons, right? And that's the same as our thrust force. Now, all of a sudden here, we're looking at our gravity and our buoyancy being equal to 5.24 times 10 to the negative 15. So, if you look at it, right, these forces, the vertical forces, gravity and buoyancy, are smaller than the horizontal forces, right? They're a lot smaller. Well, I wouldn't say a lot. I mean, yeah, they're pretty small compared to the horizontal forces, because the horizontal forces are equal to 2.8 times 10 to the negative 13 newtons. These are equal to 5.24 times 10 to the negative 15. So, because these are smaller forces, right, they're a lot smaller than the horizontal forces, then that means that the vertical forces are too small to be significant. Because they're a lot smaller than our horizontal forces. Yeah, they're less because this is 5.24 times 10 to the negative 15, and these are 2.8 times 10 to the negative 13. So these are larger forces. The drag and the thrust are larger forces than the buoyancy and the gravity. So the buoyancy and the gravity, those vertical forces, the forces pointing in the y direction, are too small to be significant compared to the horizontal forces of drag and thrust. So vertical forces are smaller than the horizontal surfaces, so the vertical surfaces are less significant. So we only want to be concerned with the x forces. Sound good? All good for problem 2? We still have problem 3, and problem 3 is long. But yeah, hopefully we can get problem 3 done pretty quickly here. But yeah, if everyone's good for problem 2, problem 3 is body fat percentage and buoyancy. So we have Archimedes' principle can be put to practical use in medicine, where it's often desired to assess what percentage of a person's body is fat. Since fat is less dense than water and other constituents of the body, we intuitively expect bodies with higher fat percentages to float more, experience a greater buoyant force. The first thing to do is measure the patient's average density. So suppose the patient is hoisted with a rope into a water tank deep enough to be completely submerged, right? The tension is adjusted so that the patient remains at rest. Then its magnitude is measured with a force gauge. So tension adjusted so that patient remains at rest. Then the magnitude is measured with a force gauge. So part A asks us to draw and correctly label a free body diagram for the patient. Draw a little center circle here, right? What forces are acting on the patient here? Because remember, they're being hoisted with a rope into a water tank and being submerged completely underwater. So we have buoyancy, yes. Is tension pointing down, though? Because remember, like, if there's a water tank, right, and they're kind of submerging them, so imagine, like, they're being... This is a horrible representation, but Let's just say that they're being like submerged in the water. This is not science. This is like torture. So yeah, gravity's downwards for sure. Buoyancy's pointing upwards, right? And then tension would actually be pointing upwards, right? Does that make sense as to why that's the case? Okay, cool. So that's kind of our free body diagram there. We have buoyancy, that's pointing upwards, right? When you're submerging something underwater, buoyant force is going to be kind of helping that object to kind of move upwards and float, basically. Gravity is pulling it downwards. The tension is pulling on that person upwards. Right, so that's our free body diagram for part A. For part B now, says the reading on the force gauge, that's the tension, it's 35 newtons. If the patient's mass is 75 kilograms, what is the magnitude of the buoyant force? So we know that F tension is 35 newtons. We know that the mass is 75 kilograms, right? And we need to figure out the buoyant force, right? So what do we need to do? Yeah, having a picture here will probably help a little bit better, but hoisted is just a weird word to use here. But basically what's happening here is, like, imagine if they were like lowered down using a rope, right? They were submerged, kind of attached to them like that, right? That's the idea, where you have tension pointing upwards, gravity pointing downwards, and then buoyancy as well pointing upwards. Yeah, not by the neck. I didn't intend for that to happen, but forgive my drawing. But yeah. So now that we're trying to figure out our buoyancy force, right? What can we do to figure that out? What are we going to do to calculate the buoyancy force? What do we need to set up? F net, right? An F net equation. And that should be in the y direction, right? Those are the only forces that we have. And so F net y, and that's equal to 0 here, because it says the tension is adjusted so that the patient remains at rest always, right? So the patient is remaining at rest. They're not sinking or floating or anything like that, right? They're just kind of at rest there. Then all these forces should cancel out. They should add up to equal 0. So F net y is equal to 0. We have Ft is positive plus Fb minus Fg, right? And so this way then we can kind of isolate the buoyancy force. We can get Fg minus Ft is equal to the buoyancy force. We know that Ft is equal to 35 newtons. Fg can be easily figured out because Fg is equal to mg. We can take 75 kilograms, which is the mass, multiply it by the force of gravity, or the acceleration due to gravity, and that gives us 750 newtons, right? So 750 newtons, right, minus the tension force, which is 35 newtons. That should give us our buoyancy force. And then that's equal to what? 715 newtons for our buoyancy force. Sound good? Cool. If everyone's good with part B, we can move on to part C. So part C now is saying we use the magnitude of the buoyant force just calculated to find the patient's average density in grams per centimeter cubed. The value you'll get is very close to the density of water, so keep your answer to the second decimal place. So if we're looking at what's it called? I've totally lost my train of thought. Yeah, we're trying to find the density, my bad. So the density of the patient, right? So you can say, this is, my bad, this is the fancy P, this is rho of the object. Let's just call that the object, and that's what we're trying to figure out, right? So what equation kind of relates the density of the object? Because we know the density of the fluid, that should be the density of the water, right? What equation kind of relates density of an object or includes density of an object? Close. Not quite the force of buoyancy, but the force of, because if we're concerned about the object itself, because imagine like force of buoyancy is equal to the density of the fluid times the volume of the fluid displaced times the gravity. Remember that equation? So there's a very similar equation, similar setup to this, but then it includes density of the object. Well, I mean, you're kind of on the right track there too, because density of the object is equal to mass of the object times the volume of the object. So if density of the fluid is equal to the mass of the fluid times the volume of the fluid, right? Or the volume displaced, essentially, then the force of gravity is actually what we're concerned with, right? Because the force of gravity gives you the density of the object times the volume of the object times gravity. And if you have density of the object, we know that's mass of the object divided by volume of object times the volume of object. Those cancel out, and you're left with mass times gravity, which is your force of gravity, right? Does that make sense right there? That relationship? But you were very close, Jonathan, about the buoyancy force. Buoyancy force only factors in like the density of the fluid and the volume displaced, volume of the fluid displaced. Force of gravity will give you the density of the object itself and the volume of the object itself. Does that make sense? Yes, no? I mean, I'm trying to get at a point here specifically that this is the second equation essentially that we're going to be using, right? Because we're wanting to find out what the patient's average density is, right? We know that the density of the fluid is 1,000 kilograms per meter cubed, right? That's the density of water. We want to figure out what P object is, right? This rho object, this density of the object, right? So if this is unknown to us, this is known, right? This is a constant, that's known. So the question here is figuring out velocity displaced versus velocity of the object, or volume of the object and the volume displaced of the fluid, right? So the idea here is that the key word is completely submerged. If an object is completely submerged in water, yes, the volume displaced is equal to the volume of the object when they're completely submerged. So if VD is equal to VO, right? Then like, since we have this buoyant force here, right? We know that the density of the fluid is 1,000 kilograms per meter cubed, that the gravity is 10 meters per second squared. Then we can figure out I keep saying velocity, the volume of the fluid displaced, and we know that the volume of fluid displaced is equal to the volume of the object because it's fully submerged. But once we figure out the volume of the object, right, then in order to figure out what the average density is, we can use this equation here to figure out the density of the object. Does that make sense? Cool. Alrighty. So we know that the buoyancy force is 715 newtons, and that's equal to the density of the fluid, 1,000 kilograms per meter cubed, times the volume displaced, times 10 meters per second squared. So that should give us a volume displaced of what? Around 0.0715 meters cubed, right? That's our volume displaced. That's the amount of fluid that is displaced by the patient. And then using that force of gravity, right? We know that the density of the object is unknown to us. The volume of the object is equal to the volume displaced, which is 0.0715 meters cubed. And then this is still 10 meters per second squared for our g. And we know that the force of gravity here is equal to our weight, which was 750 newtons, right? So then we have 750 newtons is equal to the density of the object times 0.715 meters cubed times 10 meters per second squared. And then we can solve really simply here for the density of the object. Does that make sense overall? The idea here is that, like, I mean, first you have to realize, like, okay, I want to figure out what the density of the object is. What kind of equation helps me relate density of the object to these other forces that I have, right? Because I know what the buoyancy force is, for example. I know what my weight is. Now, I know that the fluid density, right, that the water is 1,000 kilograms per meter cubed, and I'm trying to figure out what this density is for the patient. Well, how can I relate density of the patient to density of the fluid? How can I relate the density of the fluid displaced to not density, my bad. How can I relate the volume of the fluid displaced to the volume of the object? I look at these two types of equations here. The reason why is that I have access to the buoyancy force. I know what the density is for water, right? From those values, I can figure out what the volume displaced is. The volume displaced should be equal to the volume of the object because the object is completely submerged, right? Or the patient is completely submerged. If they're completely submerged, VD is equal to VO. Well, since we have VO now, right, we should be able to get our density of the object using the second equation there. Matthew, did you have a question? Sorry. Mm-hmm. So you're asking why, like, we needed to use both equations? So why FG? Okay, so FG, right, is our weight here. When we're asking about the density of the object, the density of the patient, because that's what we're asking for here, the average density of the patient themselves, not the density of the fluid, the density of the patient, right? In order to figure out the density of the patient, the density relates to the mass of the patient divided by the volume of the patient, right? So that's like VO and the mass of the patient, right? So that's going to help us get our density of the patient. Now, how does mass relate to anything that we have here? Well, we know that the patient's mass is going to relate to their force of gravity, right? Because Fg is equal to mg, right? And so if Fg is equal to mg, this m right here, this mass, a way to derive this equation, the Fg is equal to the density times the volume times the gravity, is if you think about it like this. Fg is equal to mg. Mass, we have density is equal to mass over volume, right? So density times volume is equal to mass. So we can just kind of substitute for mass, put in density times volume, and density, we define it as rho, right? That little fancy p. So density of the patient, or the object, right? Times the volume of the object, times gravity, density times volume should give us mass. So if we were trying to figure out what the density is, right? Well, we have our mass, and we can figure out our volume. technically here, both the density and the volume are unknown to us, right? Until we realize that in the context of the problem, that since the patient is completely submerged, the volume displaced should be equal to the volume of the patient themselves. Well, then we have a couple things that are unknown. We don't know what volume displaced is. We don't know what the volume of the person themselves is, and we don't know what the density of the patient is, right? Those are like our three unknowns, basically. Well, since we know that the patient is completely submerged, VD should equal VL, right? VD should equal VL, right? And we know that we have our density of our fluid, the water, is 1,000 kilograms per meter cubed, right? So this is just a matter of looking at all our variables here and kind of figuring out which equation to use or how we can relate all of these values together. How can we relate volume of fluid to I keep saying volume, density of the fluid to density of the object? How do we relate the volume of the displaced of the fluid to the volume of the object itself, right? Sure, we know that density is equal to mass over volume, right? But we're not aware, for example, of the mass of the fluid. So if we wanted to figure out mass of fluid, we don't know what the mass of the fluid is. So we can't really use that density is equal to mass divided by volume equation. What we'd have to do then is relate it to whatever forces that we have, right? So if we're looking at the density of the object, density of the patient that we're trying to figure out, but we don't know, for example, that we don't know the mass of the water, right? Because essentially here, density of the object is mass of object over volume of object, right? Density of fluid is mass of fluid divided by volume of fluid, right? Well, we know that the volume of fluid should be equal to the volume of the object, right? We know that the mass of the object is that 75 kilograms, but we don't know what the mass of the fluid is. So we can't really use the mass divided by volume is equal to density. The only way we can relate mass, volume, density together, right, is by integrating these types of equations here, because we have access to the force values. We know what the forces are. If we know what the forces are, we know some values here that was like, we know that the density of the fluid is 1,000 kilograms per meter cubed. We know that the gravity is 10 meters per second squared. We know what the buoyancy force is. That can help us figure out the volume of the fluid here, volume of the fluid displaced. So if we go back to our little equation here, volume of fluid equals mass of fluid divided by volume of fluid. Well, we know the volume of fluid now, so then we also know what the volume of the object is. So we have volume of fluid, volume of object, check, and we know that the mass of the object as well is 75 kilograms. Still, we don't know what the mass of the fluid is. We don't need to know that, right? Because we can still relate density, volume, and the forces together, right? So if we have that buoyancy force, that's 715 newtons, we can set that equal to the volume of, or the volume displaced of the fluid times the density of the fluid times the gravity. Solve for our volume displaced. We know that since the object is completely submerged, then the volume displaced is equal to the volume of the object, right? So now we can use this second equation here, where we now know that the volume of the displaced fluid is equal to the volume of the object or the patient themselves, right? So then we just plug in our volume displaced here to the volume of the object, plug in the rest of the values that we still have access to, and then from that we can figure out our density. Does that make sense? The whole idea of like figuring out what values to calculate, what to set up, which equations to use, is really just a general, broader context of looking at what do I have access to and what do I don't have access to. So if I just wanted to like think about density, like I said, I can just do, okay, density of the object is mass of the object is over volume of the object, right? Well, I know what the mass is. Oh, can I figure out volume? I know that the volume is equal to the volume displaced, right? Well, okay, volume displaced, cool. I mean, I can try and figure that out, but if I want to relate it to density of the fluid, mass of the fluid divided by volume of the fluid, well, I don't know what the mass is. So it's tough for me to relate masses to masses, volumes to volumes, densities to densities. So I don't want to think about masses anymore, right? So I want to figure out a way to relate my known values to my unknown values in a way where I am able to calculate some of those unknowns using the values that I have access to. So since I have access to buoyancy, and I know that the buoyancy force is equal to this, right, that can help me figure out my volume displaced. Since the object is completely submerged, I know the volume displaced is equal to the volume of the object, right? So that gives me this point, and I have the gravity. I also know that my force of gravity, since I have that mass from earlier, I can figure out the force of gravity, which is 75 kilograms times 10 meters per second squared. So then I can easily figure out my density of the object. So it's kind of a runaround, but it's just looking at how you can relate the buoyancy force, especially since they said use the magnitude of the buoyancy force to find the patient's average density. Well, buoyancy force, we know that is equal to the density of the fluid times the velocity, volume of the fluid displaced times the gravity, right? Well, I figured out the volume now of the fluid displaced, knowing that it's completely submerged, it should equal the volume of the object. Well, now that I have the volume of the object, what do I do? Well, you can set up this equation since we know that force of gravity is equal to mg, mass is equal to density times volume. So we can put in the density of the object times the volume of the object. Volume of the object is the volume displaced. Multiply these known values together, divide them over to get your density of the object. Sound cool? Hopefully that makes sense. But yeah. Do you understand that now, Matthew? Okay. Is there something specific that you're still not quite getting? Or do you just need a little bit? Okay, go. Exactly, yep. Yep. Okay, cool. And if you need to, like, obviously, like, you have access to these recordings later, and I upload them as soon as possible. So if you want to, like, you know, maybe I don't know how fast I talk. I don't usually go back and watch my videos because I hate hearing my voice. But if you want to put it, like, on, I don't know, 0.75 times speed or something, you want to slow it down and kind of play it back later on YouTube or on Google Drive, then be my guest, and that'll hopefully help you kind of, like, process it a little bit more, because I know it's a lot to take in. But yeah, if everyone's good for C, we can probably move on to D. Everyone else good as well? Good. Cool. All right. So part D is saying now that we have the density, we need to correct for other effects like the air trapped inside the patient's lungs and gastrointestinal tract. There's a handy formula incorporating these additional effects, allowing us to calculate a person's body fat percentage, knowing only their density. So fat percentage is equal to 4.95 divided by the density minus 4.5 times 100, where the density is given in units of grams per centimeter cubed. I just realized for part C, I just realized we never even calculated what the density of the object is. So I'll just kind of expedite things real quick. What you get here for your density of the object, since we're using kilograms per meter cubed, right? You're going to get an answer in kilograms per meter cubed. But then you need to convert it to grams per centimeter cubed. So you should end up with a density of the object equal to 1.049 grams per centimeter cubed. Which that would just be equal to like 1,049 kilograms per meter cubed. And since they want us to keep it to the second decimal place, then this should just be 1.05 grams per centimeter cubed. But yeah. For part D now, they're literally just asking us to plug in the density that we got from C into this little equation here. Right? So they say handy formula incorporating these additional effects, allowing us to calculate a person's body fat percentage. So fat percentage, this is what we need to figure out. So fat percentage is equal to 4.95 divided by that density we figured out earlier, which was the 1.05 grams per centimeter cubed. Subtract that 4.5 and then multiply by 100. Let me know what you guys get for that as well. %. Yeah, about 21.4. I think I initially used 1.049, and so I got like 21.8, but like depending on your rounding, like yeah, you guys are probably right. So 21.4% is about right. But yeah, that's part D. Just really just kind of taking some values, plugging them in from part C, and you're good to go. But then E and F are a little bit more long-winded in terms of the explanation kind of idea there, because E is saying initially the patient is suspended in the air above the water, and as they are lowered and slowly submerged in the tank at a constant velocity, how does the buoyant force change over time? So, excellent. So the buoyancy force slowly increases over time, right? We know that the buoyancy force from that last problem is equal to the density of the fluid times the volume of the fluid displaced times the gravity, right? So buoyancy force is equal to the density of the fluid times the volume displaced times the gravity, right? Now, the density of the fluid and the gravity, those are two constant values. But as you lower the patient into the tank, more volume of the fluid is displaced, right? So like imagine, I don't know who does this, but imagine you take an ice cube and you were to try and dip it in some water, right? Well, normally you just throw the ice cubes in and you see that water level kind of elevate. That's the volume displaced, right? And so if we were to think about this and just like dip some ice cubes in, like just theoretically, if we were to do that, right, you would slowly kind of see the volume displaced kind of increase, right? Because we went from zero volume displaced, just the water there without any ice cubes in it, or the water there without any patient in it, right? To all of a sudden submerging more of the patient, submerging more of those ice cubes, you increase the volume displaced, right? And so volume of the water displaced by the patient increases, so the buoyancy force increases with time. So when the patient is completely submerged, like Jonathan said, the buoyancy force then becomes constant at that point, once they're fully submerged. Because when they're fully submerged, at that point, you would have your buoyancy force kind of, I guess, well, not, yeah, I don't want to say equal to your, well, I guess, yeah, okay. Yeah, it would be technically, I'm trying to think about it, because we know that force of gravity then is equal to the density of the object or the patient times the volume of the patient times gravity. Once they're fully submerged, these points here are equal, but the fluid and the object might not be. But they already said that the patient's average density earlier in the problem is, I think they said it was going to be really close to the density of the water or something like that. I can't remember. I Yeah, I don't remember exactly if they said that somewhere, but anyway, if your buoyancy force is greater than your gravity, you're going to float. If it's equal, you stay in place. If gravity is greater, then you sink, right? And you have neutral buoyancy when you're completely submerged, and your buoyancy force is then equal to your force of gravity. But yeah. So does that make sense for E? That the buoyancy force slowly increases over time, because you increase the volume of the fluid displaced. And so as you increase that volume of this fluid displaced, right, you increase your buoyancy force little bit by little bit until the patient is completely submerged. Yep. Yeah, so like, yeah, as the patient is lowering in the water, right, then your buoyancy force increases because the volume displaced is increasing. And then what they were saying here is the tension is adjusted so that the patient remains at rest, because you have two forces pointing in the y direction, right? If the tension is too much, then the person will be pulled upwards. So they might need to lower the tension a bit as the buoyancy force increases, so that buoyancy plus tension still cancel out gravity. That's the idea here. Does that make sense? Okay, cool. So let me actually, you know what? Because I know explanations can be a little bit weird, and I don't want to leave you guys without like a set explanation for it. I'm gonna type it out because I write a lot slower than I type. So buoyancy. I like red, so I will change the color here. So buoyancy force slowly increases over time. Buoyancy force is equal to FB is equal to the density of the fluid times the volume displaced times gravity, right? And then the density of the fluid and gravity remain constant, right? But as more of the patient is submerged, right, the volume of water displaced by the patient increases over time. Thus, well, I guess, yeah, basic, that's it. And once the patient is completely submerged, then the buoyancy force becomes constant. But yeah, that's kind of a summary of what was said there, especially if you're kind of looking online on the YouTube, and you're kind of like, okay, why doesn't he have anything written down? That's basically the explanation there verbally that I said, and then there's it written. So is that cool for part E? Cool. Part F is as the patient is being submerged in the tank at a constant velocity, tension force is changing over time too. Explain why. So I actually gave the answer to this earlier too when I was talking with Matthew about it, right? Because as the patient is submerged, we know that the buoyancy force is increasing because their volume displaced is increasing, as we said in part E. But as the buoyancy is increasing, right, and the gravity is constant because of the patient's weight, right, that gravity is not changing. As we increase buoyancy, tension is there too. So Ft plus Fb, right? Remember when we said earlier that you have two forces pointing in the y direction? They have to cancel out to equal Fg in the opposite direction. So if that buoyancy force keeps increasing to a certain point. Let's say that the force of gravity is 500 newtons, right? And the buoyancy force obviously went from 0 newtons, right? Because it was suspended in the air, from 0 newtons to 100 to 200 to 300, for example. And then tension force applied an extra 300 newtons, right? Well, that's 600 newtons upwards and 500 newtons downwards. Downwards. There we go. So what that means is that you're going to have a net force upwards. We don't want that. We want the patient to remain at rest, right? So we want the upward forces to cancel out with the downward forces. So as that buoyancy force is increasing, we have to be careful about the tension force, right? Remember how it was funny and all at the beginning that I drew it in a way where the person looked like they were being, I guess, hanged into that tank? Well, that's not funny because if the tension force is too much, well, I guess there would be a net force upwards, right? We don't want that. We want the patient to remain at rest. We want to relieve some of that tension, therefore, right? In order to make sure that the forces are still canceling out in the y direction. So, in that case, if we kind of think about it, right? Let me write this down here real quick. So, as the patient is being submerged, we know that the buoyancy force is increasing. As volume displaced by the patient is increasing, right? And then we can kind of set up an F net equation, right? We can say that F net Y is equal to 0 because the patient's at rest, and that's equal to the F tension force plus the buoyancy force, that's both in the positive y direction, minus our force of gravity. And so when there's no acceleration, no net force, right? F net Y is equal to 0. Therefore, therefore, Ft, the force of tension, is equal to the force of gravity minus Fb, right? If Fb continually increases over time, right? So if Fg, for example, like I said, was 600 newtons or something, and Fb goes from 0 to 200 to 300 to 400. So you just took 600 minus 0, that's 600. 600 minus 200, that's 400. 600 minus 300, that's 300. What do you notice to the force of tension? If Fb continually increases over time, then the force of tension has to decrease to maintain a balanced F net of 0. So as the patient is lowered at a constant velocity, 0 acceleration, the buoyancy force increases. If the buoyancy force increases due to the volume displaced being increased, there has to be a decreasing tension force to still maintain a net force of 0 in the y direction. Does that make sense? As the Fb increases, so the buoyancy force increases, so therefore the tension of the rope has to decrease, right? Because Ft is equal to Fg minus Fb. Fg is just the weight, that's constant, right? The patient weighs a certain amount. As the force of buoyancy increases because the patient is being lowered in, right, the volume displaced is increasing. So as Fb increases, your Ft should decrease in order to maintain a net force of 0. Because we can see here, for example, if we were to look at the F net Y here equation, right? If Ft plus Fb minus Fg is equal to 0, right? Let's say that Fg is 600, right? Minus 600. Well, if Fb is 0 initially and Ft is 200, for example, let's say that's 500, for example. 500 plus Fb, which is 0, minus 500 for our gravity, right? If Fb starts to increase, let's say that's 100 now, minus 500, right? You can see here that this gives us a net force positive of 100, We can't have that. We want the F net force to be 0. We want the patient to remain at rest. So we have to start decreasing this tension force, right? Because this is tension. This is buoyancy force. This is gravity, right? Gravity maintains the same because the patient weighs the same. If we start to increase, right, the buoyancy force from 0 to 100, if we go down to 200 now, minus 500, right, then we have to decrease the tension force even further, right, to 300 in order for us to still cancel out, because then we have 400 plus 100, that's 500, minus 500 is 0. 300 plus 200 minus 500 is 0. We always want the answer to be 0. We want the F net Y to be 0, so there's no motion. There's no net force in the Y direction for the patient. So you can see that as the buoyancy force is increasing from 0 to 100 to 200, tension is decreasing from 500 to 400 to 300. So if FB continually increases over time as the patient is submerged into the water, force of tension has to decrease to maintain a balanced F net of 0. Sound good? Cool. All right. If that's good for everyone, that should be all of the written homework. I had some people ask about the online homework. I'm a little over time at the moment, and I don't think I'll be able to quite answer questions right now about the online homework, just because I have some additional work to do. But I'll end the recording here in a sec. Monday, I don't think so. I tend to refrain from Mondays like having a session then because it's a little chaotic. But once again, like I'm always available via email or if you want to DM me on GroupMe, and I'll try my best to get back to you as soon as possible. And those of you who have already asked me questions before, you know that I tend to reply usually pretty soon. Like I'm usually pretty good about replying to emails, and so. But yeah, I mean, just send me an email, shoot me a DM if you have any questions. I'll be more than happy to answer any of them. But in terms of like sitting down and like doing a whole session for like the online homework or for like specific questions, like additional things like on Monday, it's a little difficult because like there's like a ton to do, and it's like very, very, very overwhelming. I tried it once and it's just too difficult, to be honest, because everyone's kind of like at a different stage. But if you want to ask me a question, like I can try and do it on my own time. It's just like having everything and trying to cater to everyone's needs is a little bit more difficult because like you might have like 10 or 11 people in a session, and they're all in different places in terms of their understanding of physics, and it's hard to like jump from person to person because I don't want to spend too much time with another person and ignore someone else. But if you just send me whatever, any questions or any things that you have trouble understanding, I will be able to like send an email or draw something up or write something down and then address your questions that way. And I think that's just a lot quicker for me personally. But I'll still have a exam review session tomorrow, and you'll see me probably like hectic tomorrow during the session because just doing a whole entire exam review for a bunch of people is just very, very difficult and overwhelming to try and manage everyone's needs and their positions in physics understanding. So, but yeah, I'll try my best. Hopefully you guys get something out of these sessions and you guys find them helpful. So, but yeah, I'm gonna stop the recording here and I'll have this stuff uploaded on YouTube as soon as possible.